Hello, once again it's David at DSES UK, and today I thought it would be worth revisiting the Arc Fault Detection Device, or AFDD, something I took a first look at over 2 years ago but haven't paid much attention to since. Neither, from what I've seen, domestically at least, of many others in the UK, seeing as 18th edition, which introduced the things to a largely unsuspecting British population back in 2018, only has them as a recommendation under Regulation 421.1.7. And so long as they're merely just recommended, retailing at a horrendous cost per unit and absent from the day-to-day stock on wholesaler shelves, then their rarity out in the wild should come as a surprise to no one. However, 18th edition Amendment 2 is currently out as a draft for public consultation, and one of the proposals therein is for that wording to be changed, mandating AFDDs for domestic circuits rated at 32 amps or less. You know, I believe I have a musical number about this. Roll VT. I always wanted to say that.
Coming up, Jimmy Savile is scouting for boys, but first a musical whimsy from two silly old farts about regulatory electrical shit. The following contains strong language and a lack of dignity or self-respect. Viewer discretion is advised.
Listen up, bitches, we have data for you. Draft for public comments open on Amendment 2. Another 80 quid book in which to get your head down. Yes, Amendment 2 is coming when the cover's shit brown. Only proper sparks will care, the rogues don't give a fuck. They don't know when to start with the regs book. Instead they spout off nonsense as an absolute skanker, making up reviews like a checker trade wanker. We're competing with those whose standards are lesser, while taking some arsehole from our NIC assessor. The pace of change of the regs drives you bloody batty, makes you go and do things a little bit twatty, like tweeting a selfie as a fashion disaster, wearing some cocksuckers discount code like Richard R. Blaster. But enough of our bitching, turn to Nigel and me, not this silly fat wanker from EGTE. What? Rocking up here without his crew, wobbling his arse out of an Isuzu. Yeah, we're gonna tell you about something new that's gonna fuck you over from 2022. According to Amendment 2's DPC, IET have got hard for the AFDD. Plus they figure it's all financial look, as they get to sell us all a new regs book. Someone's getting rich off this and it ain't me. More red tape and arsehole is the way it seems to be. Yes, IET don't care too much for us street grunts, so long as they can coin it in out of us. What rhymes with us? Grunts? Elephants?
Punt.
Mm-hmm. I told you we should have planned this instead of just making it up as we went along.
Well, it's ruined now.
It's gone.
Yeah.
Oh, that sounded better on paper, and let me just add that lip syncing is harder than you'd think. Indeed, I have a newfound respect for Milli Vanilli, who managed to bag a Grammy doing it 30 years ago. Anyway, draft for public comment is indeed open on the proposed changes to 18th edition Amendment 2, which is itself slated for release on 28th March 2022, and AFDDs command a key and controversial slice of the action. So let's talk arc fault detection devices, and despite previous coverage from myself and better folks than I across other channels, many street sparks still don't quite understand the role of the humble AFDD. So I'm going to perform a quick run through here, then show you how I blew the dust off my 2018 Siemens unit to incorporate it into the test rig of my twat cave, and how I can now reliably demonstrate its operation with 2 new items of equipment I have built. The first being my arc fault chamber. Oh yes, sounds very cool for what is essentially a plastic box, some copper pipe and, yes, more bloody Lego. Those who patiently sat through my video from 2 years ago may well remember a ridiculous Lego contraption I knocked up back then to try and reliably actuate my AFDD. Not entirely successfully, it has to be said. I also demonstrated it at Tresham College with Gaz and Joe, even less successfully. However, my new and improved unit here is 100% guaranteed to operate the thing when I want to demo it. Before we look at that though, let's have a quick recap on what an AFDD is and how it's probably going to complicate your life from 2022 onwards if these draft changes go through. We are, of course, all familiar with our traditional protective devices. A fuse or breaker will cut the supply in an overcurrent event to prevent the wiring from heating up and melting, be that a fault such as a short circuit between line and neutral or line and earth, or an overdemand, for example, plugging too many electric heaters into a socket circuit when the central heating packs in. Yes, a fuse or breaker keeps your wiring from getting too toasty. A residual current device, or RCD, known also by the arguably more sensible name of ground fault circuit interrupter, or GFCI in other corners of the globe, will pull the power should current leak out of circuit, whether that current happens to be leaking into neighbouring wiring, extraneous conductive parts, into protective conductors, or through you as you perhaps grip a faulty electric towel rail with one hand whilst jacking off with the other, leaving your cum face permanently etched onto your corpse as it lies twitching on the bathroom floor. Whatever, I'm not here to judge you perverts. Suffice to say, the RCD will detect such a leak of current out of circuit and trip off before the touch voltage gets to 50 volts, if it's rated at 30 milliamps and doing its thing as intended. An RCBO, of course, is simply both types of device combined into a single form factor. So, if we already have devices that protect the wiring and devices which protect us, what on earth is the ARC fault detection device for? And just how have we Brits managed this long without the buggering things? Well, there's one of the kind of fault that won't bother our previous protective devices: arc events. Like a fuse or breaker, the AFDD is there to protect the wiring rather than to protect life, although if it prevents an electrical fire, then that would serve to keep you safe indirectly, of course. The kind of fault we're concerned with here is your typical loose connection or fractured cable core, something where there's no clean gap to open the circuit, but rather a high resistance joint, perhaps a tiny air gap whose resistance can be overcome by the EMF pushing against it, causing the air to break down into a very localised, very high temperature plasma arc that, if left to its own devices, may thermally damage equipment or ignite surrounding materials. Arcs can occur in series or parallel. A series arc would be a loose connection or a fracture along a single conductor. A parallel arc would be between conductors where insulation may have been compromised. We'll look at some series arcing shortly, but I can quickly demonstrate a parallel arc using an insulation resistance tester, in this case the relatively new TIS MFT Eco, an example of which I've managed to get hold of. Look out for a full hands-on demo coming soon on this fellow, which is a more affordable sister to my trusty MFT Pro. I've set the insulation resistance function on this thing to 1000 volts just to ensure maximum welly. It's connected to a piece of 6mm 6240Y twin and earth with exposed cores closely spaced at the other end. Just to be sure of catching something on camera, let's sluice it with a little splash from a bottle of the old homebrew. Actually, I'll sluice myself a little too, if you don't mind. An acquired taste. Anyway, with my tester connected to the cable, I shall push the go button and we should be able to see some fireworks as the test voltage arcs across the liquid medium between the cores. Christ on a bike! Shit. What the hell did I put in this stuff? Oh,
Fire
bollocks.
detected in Twat Cave.
Alright, set off the old Halon system. I've got to get out of here.
Evacuate compartment for Halon 1301 discharge. In 3, 2, 1. Flooding commencing. Evacuate. Evacuate.
And we're back. Sorry about that little hiccup there. I should perhaps stick to salt water to demonstrate this sort of stuff. Speaking of such, I've dabbed a bit onto the ends of this new piece of cable and will now repeat the experiment to show some zapping, hopefully, between the cores. It's one of those blink and you'll miss it deals, I'm afraid, but I'll try and get something captured, zoomed in shortly. Anyway, let's give it a go and see what we can see. Did you see that? There was a little bit of a flashette there. Let's just try that again. Oh, that's a good one, yes. Look at that zapping away. And sure enough, the tester reports a failure condition. Not okay, it says. This is perhaps a crude example of a parallel arc fault, but it's an easy way to show what we're talking about. Of course, a cable saturated with an external influence such as this in real life would see one of our traditional protective devices operate in short order. Again, this is a demonstration only to visualise arcing between cores, so let's not get too quippy in the comments here. Just for shits and giggles, for a more dramatic demonstration of an electrical arc, I once again give you my 10 kilovolt Jacob's ladder. This thing consists of nothing more than 2 barbecue prongs, each attached to the output of a step-up neon sign transformer and separated by an air gap. An EMF of 10,000 volts is enough to overcome the insulation resistance of the narrow air gap at the bottom of the prongs, with a brief audible crack as an arc forms through the air, closing the circuit and allowing current to flow. The arc then rises with the heat, expanding as the prongs pull further apart to the point where the insulation of the air gap is too great and it snaps, breaking the circuit before it all starts again. You know, I'm sure next door loses their Wi-Fi whenever I fire this bastard up. Dramatic though it is, the kind of arcs our AFDD is going to detect and prevent today are much smaller, as you'd probably hope. If you see something like this on your average domestic installation, then it's perhaps best to leg it down the pub and deny all knowledge, especially if it was your fault. AFDDs are nothing new. Our stateside cousins, for one, have been using them for years. Yet somehow in the UK we've muddled along without them until now. When I got my tit squeezers onto this one back in 2018, I made a video with my scientific Lego apparatus to attempt to demonstrate it in action. With little success, it must be said. What I didn't admit to in that video was that I spent quite some time trying to cause this thing to trip without getting anywhere. What I had to resort to, and this was shown in the video, was applying salt water to the wires in order to get it fizzing enough to simulate the correct kind of arc signature that would fool my AFDD into tripping. Yes, arc signatures are where it's all at, as a bit of arcing action is not uncommon when we operate a mechanical switch, relay, contactor, or even where you have an electric motor, such as in this drill, whose brushes naturally arc and spark as it operates. Obviously, we don't want our AFDD to be tripping off the power every time we flick on the lights or fire up the blender. So what our AFDD is looking for, as it monitors the live wires, are the telltale signs that arcing is occurring, and that the arcing is unnatural, for want of a better term, than it simply being down to everyday use of ordinary electromechanical appliances. Like an RCD, an AFDD has a test button. And at the time of recording, I'm not aware of any test instrument that can prove satisfactory operation of an AFDD by injecting or simulating a signature arc. So I had a quick crack at making one. Actually, I made 3, one of which was unsuccessful. Still, I expect you want to hear all about it, no? Well, fuck it, I'm rolling with it anyway. My AFDD is branded as Siemens, and you may recall in my old video that I had it paired with a Crabtree Starbreaker Mini RCBO. Well, today it's been paired with a 16 amp Wilex RCBO, but before you have a bash at me about mixing brands, type testing and all that poppycock, both Crabtree and Wilex are Electrium marks, and Electrium are owned by Siemens. In fact, the Starbreaker and Wilex RCBOs are identical stablemates, aside from the former having a plug-in buzzbar connector and the Wilex using the traditional cage clamp. Therefore, this AFDD is designed to mate with either model of RCBO. It's only branded as Siemens as it was new to market when I got it, and localised labelling wasn't yet in place. Notice this mechanical key on the side of the unit. When mated with an RCBO, this key sticks in the bumhole, for want of a better word, on the side of the RCBO. When the AFDD trips, it rotates 90 degrees, which trips the RCBO and stops it from latching back on until the AFDD has been mechanically reset. This AFDD is an add-on unit, of course, but the market now has devices providing arc fault, overcurrent and earth leakage protection in a single module form factor, albeit at rather hair-raising costs at the time of recording. Check the eFix link in the description to see Gaz showing one of these bad boys off. On my model, a steady red light indicates normal operating condition. You'd think they'd use a green LED, but maybe red ones are cheaper, I don't know. Anyway, this indicator also acts as the test and reset button and will flash yellow if the thing is tripped off because of an arc fault. If it trips off and the indicator shows the normal red illumination upon restoration of power, then the trip event was down to the RCBO side of the device, i.e. an overcurrent or earth leakage event, in which case you don the Sherlock Holmes deerstalker and get busy trying to find the nature of the fault, as with any normal RCBO trip. The single module devices, at least those from Electrium, which are the only ones I've played with, are a little cleverer with their LED indications, with a single pulsing flash for an arc trip and a triple pulsing for a residual current trip to aid in fault finding. Both this and the single module will also provide visual indication of overvoltage and a failure of their self-test function, something the Electrium models perform internally every 15 hours according to Gaz on eFix. Let's take a closer look at this latest addition to my wall of interesting cack, my AFDD arc chamber. As you can see, it has a viewing window and integral illumination for any interested observer to see the mechanics in action, actuated as they are by this control wheel on the underside. That light in there, incidentally, is interesting in of itself, as I believe it's a cold cathode tube, but one which runs directly from 230 volts without the need for a driver. I've got a handful of them from about 20 years ago and figured one would be ideally employed here. A rather unusual item, I think. Anyway, back onto topic, and with the camera zoomed in, you can see that in there are two brass contacts, the upper one being fixed, the lower one moving up and down as I adjust the control wheel. Like my original Lego thing then, the job of this jobber is to mechanically make and break a electrical contact to hopefully create an arc event that the AFDD can detect. Unlike my previous Lego contraption, which didn't work unless brine was slopped onto it, this example does the do without any undue external influences. So what's changed between my last Lego model and this one? Well, only the cross-sectional area of the contact points. Observing videos of Eaton and Electrium AFDD test rigs in action, the motorised Electrium one being especially tingly about the balls, the only thing I could see that they had which I previously lacked was a wide point of contact between the live parts. I also saw JW use brass stop ends for his AFDD demo rig, so I ripped him off. But don't tell him, it'll be our little secret. In fact, it seems contact area is so critical for a test rig that when I built this thing I could only find one stop end among my plumbing parts originally, so the upper contact was just the end of a copper pipe. But it wouldn't work reliably. Only by tootling off to Toolstation to pick up and install a second stop end did it then work as expected. Let's have a play with this son of a bitch, and for the sake of filming I'm going to remove the cover. This instrument will create a series arc, of course. The line wire from the AFDD passes to the upper contact, while the wire from the lower contact attaches to this socket outlet above. The neutral from the socket then comes back to the AFDD. A neon indicator within permanently illuminates whenever the AFDD is powered, just to show that the thing is live and dangerous, although the cathode inspection light is independently controlled. If I plug in a load such as this fluorescent inspection lamp and then lock the contacts together, we can see it illuminates. Let's put that down on the floor there, and if I adjust then the position of the contacts, then hopefully we can get to see a bit of sparking action going on in there. Let's get the camera zoomed right in to try and see that. If you look around the left side of the brass contacts, if it's picking up on camera, it's very small, there's not a lot to it. It only takes a minor adjustment to make or break the circuit. In fact, you might be able to hear it as much as you can see it. There's a bit of a humming noise to it. That's pretty sustained, isn't it? It's very small there, there's not a lot to it. This is a 23 watt lamp, so at 230 volts that's about 100 milliamps. That's not a lot of welly, and I only need a gap of micromillimeters for it to go open circuit completely. Even if I can get a bit of arcing action going on here, as we've just seen, it seems the load just isn't enough for that all-important arc signature we're trying to generate in order to force the AFDD to react. Okay, so we need something with more balls, and nothing is more balls than doing the ironing. This iron is a couple of thousand watts, so a good 8 or 9 amps. At present, the brass contacts are pressed together, so inserting the plug should fire up the iron. And indeed, my clamp meter reports 9 amps being drawn there. And if I adjust the brass contacts, there we go. The AFDD has caused the RCBO to trip off. And as you can see, I can't mechanically switch it back on because the AFDD is mechanically holding it open, as we saw earlier. This inability to reset the RCBO along with the AFDD test button being pushed out tells me that the trip was initiated by the AFDD and that the RCBO isn't off as a result of an overcurrent or earth fault event, nor has it been manually switched off. With the AFDD reset, I can now also reset the RCBO. And there's our flashing yellow light to indicate it was indeed an arc fault which tripped the power. By pressing the button again, we're restored to normal operating condition. So we've seen that the 23 watt inspection lamp was too small a load to actuate the AFDD, while the 2 kilowatt iron operated it easily. So using this apparatus, what size load do I need to plug into this socket to demonstrate operation reliably when I want to impress all my loads of girlfriends? I'm going to find out with the aid of a hairdryer whose power consumption is dependent on the chosen setting, up to a maximum of around 2 kilowatts. This thing has 2 speed and 3 heat settings plus a cool or hot option, and I'm going to use this meter each time to set the power draw. Okay, let's start on the lowest setting first, so that's cool. We've got heat setting 1, speed setting 1. $234 watts. Let's plug that in there and we shall zoom in. See what we can see. Okay, some fireworks there, but nothing troubling the AFDD. Let's notch this up a little. So we'll stay on cool, but heat setting 3, maximum speed. $451 watts. Let's zoom in again. Well, there's definitely some fizzing going on there, but we're still not getting. I don't know why I can't get the hang of that bloody zoom button. I keep going the wrong way. Right, let's notch it up even further. Heat setting 2 on hot, single speed. Okay, we're just shy of 600 watts there. Sure as shit looks like localized high temperature arcing to me, but we're still not fooling it. We're going to have to take this up even further by the looks of it. Let's go for hot single speed heat setting 3. 1.5 kilowatts. Now we should be talking, surely. That's got it. No messing about there. And again, there's our yellow indication to show it was an arc trip. Still not completely convincing though. We do have one more option on this, which is to go all out balls to the wall, hot, heat 3, speed maximum. What's that going to be? 2 kilowatts. Yeah. Okay, let's zoom in for this one. This should take no time at all. And indeed, it doesn't. There you go. So at that sort of loading, pretty reliable operation. In fact, just do it again, just to show it's reliable. Works for me. Now all this isn't to say an AFDD is not going to work with sub-kilowatt loads. Remember that this isn't a real-world example or even laboratory conditions. It's Lego, for fuck's sake. Nonetheless, I do wonder why a device that's supposed to trip off on loose connections doesn't do so here, despite demonstrable sparking action, unless there's a significant current draw. It's all very well saying that what we're seeing here are sparks, not arcs, but small, localised, high-temperature events from loose or high-resistance joints are exactly where heat damage will occur, and the job of these things is apparently to prevent that. But I know of better men than I, whose opinions I respect, and who have doubted these things and then been converted as to their efficacy. So I'll toe the line that AFDDs are effective and have their place. Anyway, enough of my AFDD demonstrator. You've seen it in action, you can see it's reliable with the right kind of loading, but what I really wanted to make was a portable AFDD test instrument. Something that could operate at the touch of a button or with insertion of test probes without having to disconnect the load circuit. At present, the only way to prove operation of the AFDD is by pushing the mechanical test button, which forces a mechanical trip. But what I want is a means of physically fooling the thing into proper operation by stuffing an actual arc up its arse. My first attempt at such a beast was an interesting failure. My second attempt was perhaps clumsier in presentation, but nonetheless successful. Let's talk about the one that didn't work, which, as it turned out, was a total overcomplication of what eventually did do the business. I wondered if I could simulate an arc fault by rapidly switching a large load on and off irregularly, and here it is in action. There's definitely some fireworks going off here, but it's not fooling the thing, and yes, I know this looks rough as fuck and downright dangerous, but this was knocked up late one evening and with parts that were to hand following a Barney with the wife, which saw me locked inside the twat cave and needing a distraction for a while. Top tip, fellas, when your affair has been revealed and your missus hits you with the teary "what's she got that I haven't" line, don't say perky tits and a sunny disposition towards oral sex. Anyway, I'm getting quite off cock here. Suffice to say that this contraption was a late night affair of a different kind, using, as I said, parts readily to hand. Although unsuccessful, I'll give you the rundown of what I was trying to achieve in my amateur efforts, just so electronics boffins out there have something to giggle over. And we start with an off-the-shelf 555 timer circuit, instantly recognisable to anyone who has ever had the need to jizz out a square wave. Resistors R1 and R2, the former being shown toward the top of the diagram, are each a kiloohm. These resistors, along with the capacitor, will dictate the duty cycle and frequency of the output. In this case, R1 and R2 are of the same value, so we don't get a nice, neat, even square wave with a 50-50 duty cycle on the output, although that could be achieved by dropping R1 to 100 ohm. But here, the output of the chip is on more than it's off. In fact, let's do the maths. Come on, bear with me. Mark time, TM, the time the output is on for, is given by the constant of 0.693 multiplied by the sum of R1 plus R2 multiplied by the value of the capacitor, which, with these components, poos out at 0.3 seconds. Space-time, TS, the time the output is off for, is given by the constant 0.693 multiplied by just the value of R1 multiplied by the value of the capacitor. In this example, it comes out as 0.15 seconds. So the output of this timer is on for twice as long as it is off. The duty cycle is then 66.67%. The periodic cycle, the total time it takes to turn on and off, is around 0.45 seconds, giving a frequency of 2.2 Hz. There's nothing too unusual about this, the only components extraneous to the timing function being a 330 ohm resistor protecting an LED, which lights in sympathy with the mark time on the output of the timer chip to provide a visual indication of its operation, and a 1N4148 diode, which I shall come to shortly. So we have a timer circuit with an output switching on and off. Let's make another circuit, identical except for a different capacitor, 100 microfarad this time instead of 220. We know that our first circuit puts out a 2.2 Hz square wave with a 66.6% duty cycle. So if we use the same calculations as before for our second circuit, this time changing the capacitance value accordingly, we can see that this timer is on for 0.13 seconds and off for 0.069 seconds or 69 milliseconds. Same duty cycle, but it's operating at a higher frequency, i.e. faster than the first timer. You'll notice the 1N4148 diode on the output of each timer. Well, that's so I can connect them together without the output of one being injected into the output of the other. This forms a primitive OR gate on the line between both diodes, as that line will be on when either timer 1 or timer 2 is on. I can feed that via a protection resistor into the base of a transistor, a BFY51 in this case. This transistor is acting as a switch, able to control a higher current load than the timers can directly, with the transistor being on whenever the output from either timer 1 or timer 2 is high. As the timers are running at different frequencies, this results in the transistor switching on and off more sporadically than if it were connected to a single timing source. In the words of Rolf Harris,
Can you tell what it is yet?
the idea here is to use the transistor to switch a relay coil with a 1N4001 diode across the coil for EMF suppression. The relay is then what controls an AC source, switching a load through the AFDD. With the circuit switched off, the load passes through the normally closed contacts of the relay, and the AFDD powers that load without detecting any headaches. When the circuit is powered on, the transistor switches on and off rapidly and unevenly because of the two uneven timing sources. The relay, being electromechanical, can't react as fast as the transistor. Nonetheless, it does stutter between the normally closed and normally open contacts, making and breaking the circuit in a non-even way. This forms my attempt to make the AFDD perceive there being an intermittent fault, such as a loose connection, and shit its pants accordingly. Unfortunately, the AFDD isn't fooled. I guess it just looks too much like a motor still, despite the fizzing going on inside that relay and the thermal damage being sustained to it. A few more minutes of operation and it'll be burned out anyway. Ah well, it would have been nice had it worked, but I didn't lose a lot of time over it. And again, not necessarily the best components for the job, just what I had rattling around. Back to the drawing board then, and in what we drunks refer to as a moment of clarity, I figured all I really needed was a modification to my wall-mounted Lego do-wicker. If I could build something with a known internal load, I could preset an arc gap without the adjustment mechanism, and it ought to work every time. No batteries required, no power source, no moving parts, no need to disconnect any downstream circuit. Simply attach it via probes to the output of the AFDD and prove its operation. And here it is. Yes, I know it looks like an old pedal bin, but this is in fact a finely calibrated laboratory instrument. And if I pop open the inspection hatch, you can see the internals, which consist of another brass contact arrangement, this time non-adjustable, and a dummy load formed by this heating element. If we look at how this is laid out, well, There you have it. 2 probes connect to the thing, line going to another brass stop end, which is separated by a tiny gap to an opposing brass contact, which itself connects to a heating element, the neutral of which connects back to the second probe port. Connect the probes between line and neutral on the output of the AFDD, and if the gap between the contacts is set correctly, then the heater will draw a large enough load, an arc will form between the contacts, and the AFDD will detect it and snap off. In terms of construction, I would have preferred to use resistors to provide the dummy load rather than a heating element, but if you try to create a 1 kilowatt dummy load with resistors, you either need a lot of small ones or some physically very large beasts to accomplish it, and that shit ain't cheap. So I went hunting around for something to hand, and as luck would have it, in my scrap bucket was a Duff electric shower with 2 working heating elements. The only trouble was, each element was 12 ohms, and if we apply a bit of Ohm's law to the thing, then we get an eye-watering 4.4 kilowatts at over 19 amps, which is rather overkill for what I want, and makes it unsuitable for use on any circuit rated below 20 amps, which is exactly what my 16 amp AFDD setup is. The solution, of course, was to tie both heating elements in series with a quick bit of soldering. That doubling of resistance halved the current to a more acceptable level. What you must appreciate when using this contraption is that these heating elements were designed to heat up cold water under mains pressure, so they get very hot very quickly. They're also not supposed to be used in the open air. That means the gap between my brass contacts is super critical. Too wide and nothing will happen. Too close and there'll be no arc. Instead, my elements will just heat right up, and within a second or two they're passing 100 Celsius and are too hot to handle. When connecting this thing, if the AFDD doesn't clock off immediately, it's imperative the plug be pulled, so to speak. Hence all the warnings on the label, which aren't there to bullshit you. Anyway, let's give it a go, shall we? I've disconnected the AFDD from my arc fault chamber here. I didn't have to because this will work under load, but I don't want you thinking I'm not throwing straight dice here. Look at that, it's even got a little hanging handle that I deliberately invented as part of this thing as well. So I've just plugged my 2 probes into it, and I'm going to now connect them to the output of my AFDD. Ready? Look at that, there it is. So I have perfect adjustment of my arc gap within this thing, because it will reliably send that off every time. Marvellous. As mentioned, I've obviously got a perfect arc gap adjustment in this thing, and yet if I do it again with the camera pointing at the contacts, you heard the AFDD snap off there, and yet there were no visible fireworks, nothing to see. A bit of a sizzling noise, but I don't know if that's a air gap sizzling or the heating element, so what's going on here? Well, the gap on this thing is tiny. We're talking paper thin, literally. A small round paper sticker has been placed in the middle of one of the contacts. They've then been pushed hard together. I spent a lot of time experimenting with this, and I'm genuinely surprised that for a 2.2 kilowatt load, the required gap for reliable operation is this thin. I mean, something even slightly thicker, such as a ring binder reinforcer, was enough to make it open circuit and do nothing at all. I also found that not all stop ends are made the same, and the best results came from one of these being smooth and flat rather than a textured finish, as the texture again reduces the CSA of the contacts when you bring them together. Weird, but true. Functional though this is, I don't suppose you'll be seeing new MFTs with the ability to test AFDDs anytime soon. I was speaking with one of the chaps at TIS about such a beast last week, and as it turns out, proper conditions for testing an AFDD involves compliance with standard IEC 62606, and the energy dissipation is way more than your current MFT is rated for. Out in the field, your only approved test operation remains pushing the button to ensure it clicks off. One more note on my 2 working AFDD testers I've built here. They both use series arcing to operate. I did figure I could perhaps dispense with the heating element and physical size of this thing by building a fixed gap model directly connected between line and neutral. That's not something I looked into for very long, for obvious reasons, the gap being even more critical to prevent a straight short circuit, which would trip up the RCBO rather than the AFDD, and perhaps with a bit of a bang. But I mention it here to stop it cropping up in the comments. Incidentally, the items I've shown here are all horrendously dangerous, so consider this one of those don't try this at home deals, you kids. I do these things so that you don't have to. AFDDs then, are they hot or not? What I find curious about the proposed change for Amendment 2 is that they may be mandated for circuits of 32 amps or less. Yet it seems to me to be the higher current circuits that would benefit the most from them. Electric showers are usually the highest load appliance in the house at 32 to 50 amps. And every year I have a healthy trade in replacing burnt out shower isolators where loose connections have arced and sparked over time to the point of thermal failure. Mandating an AFDD for something like a 6 amp lighting circuit, but not a 40 amp shower, cooker or EV charger, seems like a bit of a nonsense. There's also the question of their efficacy on ring socket configurations. A bad connection on a ring itself isn't likely to cause an arc event, as the current from an appliance connected at any point has an alternative path of a lower impedance from and to the consumer unit. That said, parallel arc faults could still occur, and series arcing is still possible if the ring has a clean second break, forcing the current through a high impedance joint, or if the bad joint is on a spur cable or an appliance flex. It should be noted, as shown in my last AFDD video, that arcing within an appliance past any kind of transformer, opto-isolator or electronics won't be detected by an AFDD, which, to be fair, is only there to monitor the supply wiring, not necessarily the load. So AFDDs do have their place on ring circuits. What troubles me about all this is the pace of change. It used to be the case that a new consumer unit was expected to last years. A dual RCD board installed in 2008 when 17th edition came in was expected to be a safe bet for perhaps 30 years. Yet we've had 17th edition Amendment 3 in 2016 write off plastic enclosures. We've got 18th edition waving the naughty stick at Type AC RCDs in favour of Type A and getting us to install SPDs. And from 2022 it looks like we'll all be putting in AFDDs. The issue I have with all that, as shown in previous videos, is with those who try and apply these changes retrospectively. I guarantee that the same dipshits who today code a perfectly sound plastic consumer unit as a C2 on an inspection, then who turns up with a pre-populated dual RCD metal screw-fix special under their arm to fit in its place, will be the same dipshits who in 2 years will be sucking air through their teeth and telling old Mrs. Scroggins that her metal dual RCD board must itself now be ripped out and replaced because it lacks AFDD protection. It's like we're on some continuous upgrade cycle. Actually, we are on a continuous upgrade cycle, but how much of it is really down to new technology being introduced in a timely fashion to keep up with our changing lifestyles and dependence on our electrical gadgets, and how much is being driven by manufacturer lobbying who, having sold you a consumer unit 5 years ago, now wants you to rip out and replace to their all-new, all-safer model with Go Faster stripes? And what will 18th edition Amendment 3 bring further down the line? An end to dual RCD configurations? Mandatory SPD installations? Banning of Type AC residual protection? The requirement for AFDDs for circuits greater than 32 amps? A return to insulated enclosures? Who knows, but the manufacturers and the EICR miscoders will be rubbing their wanking clamps together and sporting pound signs in their eyes, you can be sure of that. The problem with making circuit protection ever more complicated and expensive is that those who have the oldest, creakiest fuse boxes still humming away in their homes are often those who can least afford to upgrade to a better standard. Although AFDD prices are prohibitively high at present, no doubt they'll drop with volume of sales once everyone is forced to buy them. However, entry-level consumer units that may have cost £60 5 years ago may easily cost over a couple of hundred in the near future if they're to comply with the latest regulations and not be made obsolete within months of the ink drying on the installation certificate. The industry risks pricing out the very people who are most in need of modernising their electrical protection, and for that reason I believe AFDDs and SPDs should remain optional for domestic installations. Otherwise, what am I supposed to do when confronted with a family surviving on the breadline a couple of years from now whose rewirable fuse box desperately needs replacing? At present, I can give costs for dual RCD, full RCBO, SPD and AFDD configurations, and they can make a price versus performance decision. If those choices are removed from us though, then there will come a point where the baseline hardware is just too damn expensive, leaving me with 3 unpalatable options. Number 1, install a basic, lower cost dual RCD or RCBO board and list the emission of AFDD and perhaps SPDs as departures on the certificate. That at least affords the client better protection, but opens me up to risk for not having complied fully with BS 7671. Option 2, walk away and leave them with their antiquated circuit protection. Or option 3, compromise on the labour cost or otherwise financially contribute towards the installation, which obviously goes against how the business is supposed to operate. I'm not a charity, and if the market dictates that I can make a profit on job A or take a hit on job B, well, so long job B. Although everyone deserves the best level of circuit protection, everyone also deserves the best tyres on their car. But you don't find garages insisting we all splash out on premium Pirellis or Michelins as a minimum. The end client needs a range of options their wallet can support, and the industry doesn't need another mandatory upgrade that allows fly-by-night EICR cowboys to go around C2ing perfectly adequate existing installations. That's the concern I've raised, pretty much word for word, in my own feedback on this DPC. If you yourself want to comment regarding the change of wording to Regulation 421.1.7, then create an account on the BSI website and use the link in the description to access the relevant page. Then click Draft Chapters 1 to 45, click Read Draft and Comment, click Chapter 42, scroll down to 421.1.7 and click Add View Comments. You have until 11th December to make your voice heard on this or any other proposed changes, for whatever it's worth. Anyway, let me know your thoughts, especially if you live in a country where AFDDs are common. How effective do you find them, and what are the pitfalls that catch you or your customers out? Do spill the beans, and thanks for watching.